Okay, so I thought it'd be useful to have a video where I work through 2 NMR questions. A lot of students find NMR quite tricky. You shouldn't find it tricky. It's a bit like riding a bike. Once you can do NMR questions, then you do really well. So I've got 2 NMR questions, and they're both taken from the OCR exam papers. Old OCR exam papers, but it doesn't matter. From the F3-4 papers, the papers are called Rings, Polymers and Analysis, and I think there are 2 really good Rings, Polymers and Analysis, 2 really good questions. Okay, the first question is taken from the 2014 paper, and the second question is taken from the 2015 paper. Okay, right, so let's start with the first question. Oh, actually, before we start with it, we're using the data sheet, the OCR chemistry data sheet, which has got the chemical shift at the bottom, and it tells you which hydrogens, which is in bold, which hydrogens, and the chemical shift at the bottom. I just want to point this, if you can just please look at this last line here, because this is quite important. It says, note that CH bonded to shifting groups on either side, and there's an example. There's a HCO, there's a HCO here, and there's a HC double bond O there, may be shifted more than indicated above. Okay, so if there's 2 shifting groups, one on either side of the hydrogen, then the chemical shift may be shifted, and we're going to see an example of that in a moment. I'm not going to keep on flicking back to this, so please make sure you've got your copy of your OCR data sheet with you too. Okay, so this question is the first one from the 2014 paper. A chemist isolates compound H. Initial analysis, so it's got the molecular formula there. So straight away it tells you from that molecular formula there's 1 oxygen. Okay, so it's either an aldehyde, a ketone, or an alcohol. Yep. Also, please look at the hydrogen to carbon ratio. There aren't that many hydrogens. There are 10 carbons, but only 12 hydrogens. So that should make you think about something as well. The fact that there aren't that many hydrogens. So that should make you be thinking about a benzene ring. Yeah. The carbon NMR has got 8 peaks, so that tells you that there are 8 carbon environments, and it gives you the proton NMR below. So therefore, as you're reading the question, you should be picking up that information. The question actually starts with part A. The proton NMR spectrum contains a peak, a chemical shift, 0 parts per million, resulting from a chemical added to the sample. State the chemical responsible for this peak at 0 ppm. So that chemical is TMS. Tetramethyl, its name is tetra for tetramethyl silane. Okay, it has the formula, so methyl, and there's 4 of them, and silane is silicon. Okay, it's from silicon. Okay, so that's the chemical. State why this chemical was added to the sample. It is the standard. It gives the standard peak. It gives the reference peak. Basically, it's telling the spectrometer where 0 is for calibration. So it gives a chemical shift of 0 parts per million. Yeah, it tells the instrument where the 0 peak is. Okay, so that's the first question. And then it tells you in the NMR, the peak at 3.7 would normally be expected at a chemical shift of 2.7. So we've got a peak here that has come out of its band. Therefore, it must have a group on either side, a shifting group on either side. Use this information to determine the structure of compound H, and there are 9 marks. Now, with these kinds of questions, these types of questions tend to be at the end of the exam paper, when you don't have much time left. And it's quite easy to miss some of these 9 marks. So a really good tip with these NMR type questions is to actually write your answer in a table. So if you write your answer in a table, you will get all the marks, and also if you can assign the peaks and get the structure, but you won't miss any of those working out marks. So I would suggest writing a table where your first column in your table is chemical shift. So you're saying where the peak is, chemical shift in ppm. Okay, I'm just going to take one of the peaks just to show you. Okay, so one of the peaks, I'm going to take this one here, and I'm going to read at about the middle. I'm going to say that it's 9.8 ppm. Okay, so I'm going to say that peak, the chemical shift is 9.8 ppm. Okay, then if you say the type of proton, so what type of proton is it? And you read this from the data sheet. Yeah, so you look at your data sheet and you go, okay, 9.8 ppm. What type of proton comes within 9.8 ppm? It's the it's the aldehyde proton. Yeah, and just copy that. So you go C double bond OH like that. Okay, then your next column, if you put your next column as relative area, which is the area underneath the peak, the integration, and that for that peak is this number here, which is number 1, and that tells you that there is one identical hydrogen. Okay, so one H has made this peak as one identical hydrogen. Well, that's kind of obvious because it's this hydrogen here, but still it's good to have it written down. And then if you write the splitting pattern and explain the splitting pattern, then you will get all the marks. Yeah, so for that peak, the 9.8 peak, we can see it is split in 3 lines. It's split in 3 lines, okay, which is called a triplet. Okay, and what does that mean? So 3 lines, it's split in 3 lines, take away 1 is 2. So that means there are 2 hydrogens on the next carbon, on the adjacent carbon. There's 2 hydrogens on the adjacent carbon. Okay, so if we go back to the table, you would say it's split as a triplet. And what does that mean? It means that there are 2 hydrogens on the next or adjacent carbon. Now, if you do this for every peak, for every hydrogen environment, then you will get all of your working out marks. So, and it keeps your answer really organized. It doesn't matter that there are lines here. You can do a draw table on top of the lines. Okay, so but for the moment, I'm going to do all the writing on the spectra because I haven't got quite as much room. Okay, so we have recognized that is the aldehyde. Yeah, so there's an aldehyde, which is consistent with the fact that there's an O there. Okay, so that's quite good. All right, so there's an aldehyde. Right, now let's look at this. So the four hydrogens on the benzene ring. Okay, so you look at the chemical shift, you look at your data sheet, and what comes at about 7.1 ppm, and that's the hydrogen on a benzene ring. Okay, so a hydrogen on a benzene ring comes at 7.1 ppm. Yeah, the 7.1 ppm, and the fact that there's 4 hydrogens. Okay, so that tells you there's only 4 hydrogens. So that tells you that there are two other items coming off. So there could be something here and something here, maybe. Yeah, okay. There could be something there, or there could be something there, or something there, Or there's a third option that could be opposite each other, totally opposite each other. Okay, like that and like that. Okay, so there's only 4 hydrogens on the benzene ring, which tells you that there's 2 other slots for something else. Okay, so that's what that information tells you. Okay, let's keep going. So I'm going to go for this one down the bottom here, this one here. So that tells you it's a CH3. Yeah, so that I'm going to say that this is a 1.3 ppm. That's close enough. Okay, so you look at the table and you can see on the table that that is a HCr. A H joined to a C joined to an R. There's the fact that there are 3 hydrogens tells you then it's a CH3. Yeah, CH3 joined to another C. An R just means another C. Okay, it's a triplet. It's a triplet. So that tells you that there are three lines, take away 1. That tells you that there are 2 hydrogens on the adjacent, on the next carbon. Okay, so a CH3 has made that peak and it's next to a CH2. Okay, so that's what that tells you. Okay, so we've got a CH3, I'm just going to draw it very clearly, a CH3, and it is next to a CH2. So these 3 hydrogens here, those 3 hydrogens have made that peak. Yeah, a CH3 next to a CH2. Okay, so then let's have a look at this this one here. So this is a CH2, and it is between 2 and 3. So it's a 2 point, let's say 2.6. Should say 2.6 ppm approximately. Okay, so it's a CH2. It's a quartet. It's split as a quartet. So therefore, that is 4 lines. Take away 1 is 3. So it is next to a CH3. Yeah, it's next to a CH3. Also, the fact that it's at 2.6, you look at your data sheet and you say, okay, what comes at 2.6? So 2.6, you have a benzene ring, a carbon, and then a H joined to a carbon. Becomes in that region. So this must be this hydrogen, which is joined to a carbon, which is joined to a benzene ring. Okay, so let me just colour this, make this a little bit clearer. I'll do a different colour just to make it clearer. So this is a HC benzene ring. Okay, a HC benzene ring has made that peak, and there are 2 hydrogens, 2 identical hydrogens. Okay, has made that peak, and it's a quartet because on the next carbon there are 3 hydrogens. Okay, we've only got 1 peak left here to assign. Okay, so that's a 2.6 ppm. We've got this one here at 3.7, shall we say? 3.7. At 3.7, this one here at 3.7 ppm. Okay, so this is the one where we had a little message. So we had a little message about this one. So it said it should normally, the peak at 3.7 should normally appear at 2.7. So when you're looking at your data sheet, you're looking for something at 2.7. Okay, at 2.7. So let's just find my data sheet. Where have I put my data sheet? Let's go back a couple of slides. Oh, sorry. So here we go. So it normally appears at 2.7. So it's something within this region. Okay, but it has shifted to 3.7. So it has 2 groups. So it must have this on one side and this on the other side. Okay, we know that it doesn't have this HCN. How do we know it doesn't have the HCN? Because there isn't an N in the formula. So it must have this one on one side and this one on the other side, because that is how the chemical has shifted by 1 ppm. So let's just go back to our drawing, okay? So we know there are 2 hydrogens. It's a CH2. Okay, so there are 2 hydrogens, CH2. Okay, it is a doublet. It is a doublet. So that tells you 2 lines take away 1 is 1. So it is next to a CH. So on the next carbon, there is a CH. Okay, so on one side it is a HC benzene ring on one side, and then on the other side of the molecule it's a HCC double bond O, and that is why the peak has shifted to 3.7 instead of 2.7. Okay, so that's your final answer. Okay, it's a little bit messy. Shall I just redraw it very quickly? I think you can probably see it. CH3, CH2, benzene ring, CH2C double bond OH. I will quickly redraw it because then I can show you the carbons. So I'm just going to quickly redraw it so we can do the carbon check. Because like I said, you need to check because it may not be in this orientation. There are several orientations it could be, because it could be this 1, 2, 3, 4, or like we said a moment ago, it could be like that, or there's also the other option, it could be 1, 2, or it could be 1, 3. So we need to just double check which one it is. So it tells you that there are 8 carbon environments. So let's just go through and check the carbon environments. Carbon 1, carbon 2, carbon 3. Then we've got some symmetry here. So this is carbon 4, this is carbon 5, this is carbon 6, this is carbon 7, this is carbon 8. So it does have 8 carbon environments, so it is not in those orientations. And that is your answer. Okay, let's just try another question here. So this is from the 2015 paper. It says the student purifies the orange precipitate. This is testing. This is 2,4-dinitrophenylhydrazine. It's testing for a carbonyl group. Describe a use for NMR in medicine. So this is the MRI scanners. Yeah, the magnetic resonance imaging scanners. Yeah, the MRI scanners is a use. State the region of electromagnetic spectrum that's used in NMR. It's the low energy radio waves. It's the low energy radio waves. Explain why CdCl3 is the solvent that we use, because the solvent does not have any hydrogen. The solvent does not have any hydrogen atoms. Remember that deuterium will not be identified because it's an even mass number. Okay, so the solvent does not have any hydrogen atoms. Remember that deuterium is an isotope of hydrogen. Deuterium. Okay, now on to the question. Oh, hang on, the carbon NMR. It says how many different carbon environments are present in the molecule. You just have to count the lines on the carbon NMR. 1 line, 2 line. Let's do that properly. So we've got 1, 2, 3. Keep counting the lines. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 lines. So that means there are 14 carbon environments. Okay, and then the next part is the actually analyzing. So you need to find the identity. You need to find the identity of L. That's what we're trying to find. Okay, so we're trying to find these two things here, basically. Yeah, and this question has got how many marks? 7 marks. This question has got. Okay, so let's look again. Drawing the table is a good idea, but I'm going to just draw it on the spectrum because I don't have enough room. Use your answer to identify R1 and R2. to identify R1 and R2. Explain how you use the chemical shift and splitting patterns. And there's in the NMR, there's a peak that doesn't appear on the data sheet, and it says it comes in the range 1.6 to 2.2. So straight away, 1.6 to 2.2, we know it is that, yeah? So we know that we have got 2 hydrogens. So what we're going to do is going to draw this molecule out. And what I'm saying is I'm going to draw this molecule, I'm going to draw this molecule here. That's what I'm saying I'm going to do now, okay? I'm going to draw this molecule out. So we have got the benzene ring, NO2. I'm just copying that molecule. Okay, and straight away, we've got an N, we've got a H, we've got an N, we've got a C, and it says here there's 2 hydrogens, so there must be here we must have a C with 2 hydrogens. Yeah, a C with 2 hydrogens. Okay, CH2. Oh, sorry, excuse me. I've done I've the wrong peak. Let me just go back here. That's not that peak because it says 1.6 to 2.2. Excuse me, I'm sorry. There we go. That's why it's important to read carefully what you're doing. It's that peak, 1.6 to 2.2. It's this peak here, which has got 3 hydrogens, and therefore it is those 3 hydrogens there, because it's the H, H, H. So what we've got is a HCCN, and it tells you it's between 1.6 and 2.2 ppm. So it's that peak. It's that peak there. Okay. We have got a single hydrogen here. So that single hydrogen is this hydrogen here. Okay, so that is that hydrogen at 5 point, looks like it's about 5.3, yeah, about 5.3 ppm is that hydrogen there. Okay, right, then we need the rest of the molecule. So we've got our R2, we've worked out R2 already. So now we need the rest of the molecule, we need R1. Okay, so the fact that you've got a benzene ring here, well, you've got 2 benzene rings because there's 2 peaks, 2 groups, and you've got 7 hydrogens. This benzene ring has got 3 hydrogens. So we must have another benzene ring, which has 4 hydrogens. Because 7, we know this benzene ring has got 3 hydrogens, so we must have another benzene ring with 4 hydrogens. Okay, so again, we're not quite sure if it's going to be 1, 2 or 1, 3, the placement, or 1, 4, the placement around the benzene ring, but I'm just going to draw it like 1, 4 for the moment. Okay, 1, 4 for the moment. And so that's another benzene ring. Okay, what other information have we got? So we have got a CH2, and it's about 2 looks like it's about 2.4 ppm, and that is the hydrogen on a carbon next to a benzene ring, and there are 2 hydrogens. So those 2 hydrogens have made that peak. It's a quartet. 4 lines. Take away 1. So it must be next to a CH3. It must be next to a CH3. So the CH3, I'm running out of colours now a little bit here. The CH3, these 3 hydrogens here, those 3 hydrogens are this peak here, which is the HCR peak. Yeah, 3 hydrogens joined to a carbon. We need to check, does this actually have the right number of carbon environments? So let me quickly clear the screen in order to check the answer. Let me just quickly sorry, excuse me, clear all the writing on the screen. We need to just check the carbon NMR. So I'm going to redraw it and check the carbon NMR. So we have got, so you've got a benzene ring, okay, with NO2 and then NO2. And then you've got the nitrogen with the hydrogen, and then we've got that, and then we had a CH3 here, the R2 group, and then here we had a benzene ring. Draw it a little bit better than what I drew before, and then we had a CH2, and then we had a CH3, and we need to check the carbon environments because we know that there are 14 carbons. So we've got 1 carbon, 2 carbons, 3, 4, there's symmetry there, 5, there's symmetry there, 6, 7, 8, and going all the way over here, 9, 10, 11, 12, there's no symmetry, 13, 14. 14 carbon environments, so that is the answer. I hope that's been helpful to you. Okay, thank you very much. Thank you.